Okay, thank you. So I'm going to present some work and analysis done by my student Gualtiero Spiro Jaeger, who couldn't be here today. So, when we started this project, Mesobob, we started with this hypothesis, partly because of what we had studied in the Bay of Bengal, that it's very fresh and stratified, and we felt that that freshwater lens would affect the SST, and through SST, the Bay of Bengal is affecting the monsoon ISO through air-sea interaction. And so this analysis is trying to look at the progression of the ISO signal and trying to see what role SST anomalies play in that progression. Okay, so as I said, the analysis is done with some NASA or satellite products. So it's a combination of products. So NASA trim rainfall, surface wind, and daily merged SST, which Rashmi actually just described. So what we were trying to look at is as the ISO event progresses, there is an SST anomaly, and this talk really follows very much what Eric Maloney described yesterday. And that SST anomaly and that rainfall anomaly, that wind anomaly, it all develops and kind of intensifies in the northern Bay of Bengal. So a hypothesis is that the northern Bay of Bengal is much more fresh than the southern Bay of Bengal, and it's able to sort of, that SST difference between the active and the passive phase, the passive and the active phase really builds up as the ISO progresses into the northern Bay. So what we wanted to look at is that if you have clear skies and you have strong shortwave forcing, it creates warm SSTs, and then that creates convection, just like Eric described. That convection causes convergence. There should be a feedback in the intensification of the monsoon ISO. Okay, so does SST anomalies affect that intensification is the question. So this is how we looked at the data. We looked at this particular strip of data, so 87 to 95 east, and we looked in the south to north direction. What's shown in color is the rainfall, and what's shown in the vectors is the winds. And we tried to see this south to north progression. So what's shown below is a Hofmöller diagram for the monsoon season in 2016. And what you can see is that these rain bands, they progress from the South Bay into the North Bay, and you can very clearly see these ISO events. Okay, so these are these ISO events that we're talking about. And these are these ISO events that we're going to try to identify in the data, and then we're going to look at them not only in rainfall, but also in SST anomaly. So we looked at 13 years of data, satellite data. This is trim rainfall that's shown here on the left. We excluded the monsoon onset period, and what you're seeing on the right is a composite of these 38 events, and you see that what's marked 0 here, day 0, is when you have the maximum rain at the equator. So each one of these events, right now they're really identified by eye, but we have also automated that to identify these ISO anomalies or events. And so when the rainfall is maximum at the equator, that's day 0, and before that is day minus something, and after that is day positive. So as you see the rainfall, as the band progresses northwards into the North Bay, it intensifies, and you get the maximum intensity of rainfall at about 15 to 18 degrees north. Okay? That's a composite of 38 events. And you can also look at the composite in SST, you can look at it in OLR. They all show this very clear progression of the events. So here is 2016, and what I'm showing here is the SST. So that's rainfall. We're looking at the anomaly from the mean June, July, August, September rainfall. That's the mean, that's the anomaly. Similarly for SST, that's the mean of the season. That's the SST anomaly. And what you can see is that in the early monsoon period, or May to July, it's extremely warm, the ocean. And then the monsoon starts, it starts to cool off. With every ISO event, you can see that there is this progression, and there is this switch between the period when the ocean is warm and the period cools, and the ocean cools off. And so this is something that Eric was describing yesterday. He says you get this warm and then a cooling of the ocean, and that has a feedback on the monsoon ISO signal. So what we wanted to do is see whether there's any difference in these events where you see a strong SST anomaly and those in which you see weak or no SST anomaly. So we identified the events which have a delta SST between this latitude and that latitude being greater than 0.75. On average, it was 1.5 degrees Celsius SST anomaly between here and here. And we differentiated that from events which had a weak SST anomaly, on average just 0.5 degrees Celsius and less than 0.75 degrees Celsius, okay? So those I call my weak SST anomaly events, and the other ones are my strong SST anomaly events. And shown down here is you can see that there's wind speed. This wind speed also goes from very strong to weak, strong to weak, strong to weak associated with every one of these ISO events. Okay, so now we took this, this record that we had of rainfall for all the 13 years. We identified the ISO events and we differentiated them into two classes of events. One with the strong SST anomaly. Those are highlighted with the red rectangle. So there the delta SST was greater than 0.75, and the blue rectangles are where the delta SST was weaker than 0.75, very weak SST anomalies. The first thing I want to say is that ISO events occur even without the strong SST anomaly. With very weak or almost no SST anomaly, you can still get ISO events. So that was, first of all, a revelation to us because we associated the ISO event with this SST anomaly. When we categorized this data with the 38 events, we found 19 which had a strong SST anomaly and 22 had a weak or no SST anomaly based on this criteria. Okay, so there's plenty of events in which there's no strong SST anomaly. Now we're going to separate those events and look at them separately. So the top row shows you the events composited now with rain SST wind speed divergence. The y-axis is latitude and the x-axis is in days. Again, 0 is when it crosses the equator, minus is before that, plus is after that. And you can see the progression of this ISO signal in the rainfall as it propagates from south to north. The rainfall, as you can see, that's the red box there shows you the strong SST anomaly. The one below is the composite of all the weak SST anomalies. And you can see that the rainfall, as far as rainfall is concerned, the ISO event occurs both in the case of strong and weak SST anomalies. There's a small difference in the rainfall or the intensity of the rainfall. Yes, yeah. The next panel shows you the SST anomaly in color, and there, of course, you can see there's a big difference between that. It goes from very high SST to weak SST during the passive and the active phase when the ISO progresses into the North Bay. Here you hardly see any difference, and this is overlaid with rainfall contours. So in each case, we have overlaid the rainfall contours so you can see the event. And look at wind speed. So if you look at wind speed, you can see a strong intensification of the winds when the SST anomaly is positive or it's warm and the winds weaken. Here you can also see an intensification and weakening, but much less difference or contrast between the wind speed. And finally, if you look at convergence, just like Eric was pointing out, when you have a strong SST anomaly, the convergence is much stronger with that ISO event. When there's a weak SST anomaly, we still have the ISO event, but weaker convergence. Okay? So now we can look at the other parameters. This is looking at the development of the rainfall. That's in blue. Again, the top panel is showing you with the strong SST anomaly. The lower panel is showing you with the weak SST anomaly. You can see that with the weak SST anomaly too, you start with this development of, here it's actually drier over the continent, wetter over the continent, over the Indian subcontinent. And then you see that there's this progression of this rain band in both cases. Here it's slightly stronger. You get now the strong rainfall here and the strong rainfall here. So some differences in the progression, but in both cases you get the ISO event. If you look at SST, which is shown above and below, that's where you see the big difference here, that the North Bay here is much warmer here, and it's actually not much difference here. So you can see that there's not much progression in the SST here, whereas here you can see the SST anomaly. So this really makes us wonder what SST is doing, okay? And it's a bit disturbing, I have to say, for us oceanographers, because we felt that the connection between the ocean and the atmosphere is through the SST, but we are seeing these ISO events in the absence of that SST anomaly. So maybe you're not fully understanding what's happening. I don't claim to say that SST, I'm not claiming that SST is not important, but maybe I'm claiming that we've not fully understood what its role is. So once again, now here we are looking at wind speed, and you can see that the wind speed anomaly, you get much higher wind speeds when there is a strong SST anomaly. As I was saying, you get stronger but much less intense signal in the wind speed with the weak SST anomaly. And finally, we are looking here at convergence, and that's the one, as Eric himself pointed out earlier, you get very strong convergence here when you have a strong SST anomaly, and that convergence is probably creating some updrafts or upwelling of the air. So moisture, so this is the moisture content, the total water column moisture, and so the red is showing you dry anomalies. So the top row again is with the strong SST anomalies. So in fact, this is when the subcontinent is exceptionally dry, the periods where the strong SST anomalies, those events have this dry period, and here the subcontinent or the land mass is actually wetter. There's a wet anomaly in the moisture when you have the weak SST anomaly. Okay? So not quite sure what all this means, but I thought it was interesting to present it in the context of something that was presented yesterday. So I'll show you a few observations from the ship that were made, and the question is now, can we tie in these observations? One thing we haven't done yet is looked at the SST, and maybe somebody has done that for the period of the ship observations from 2018, but I'll show you some of the radiosonde data, which Emily helped procure along with many other PIs. Joe Fernando was one of them that was responsible for this data set. And this was plotted up again by Gualtiero. And so this is showing you one of those drifts. Emily described to you that there are 4 drifts. The ship went south, released the radiosondes, and each one of these is a radiosonde release. So this is the radiosonde going up here. Here's the balloon going up. This is another release, another release, another release. And what we are looking at now is a SCUT plot. Again, not something I understand very well. I'm not an atmospheric scientist. That's temperature, that's dew point. When there's a big difference between these lines, you can see that the atmosphere is drying out or becoming more moist. So that's what I'm looking for. So what we did is we broke this this period up into 5 different. This is before the rains. There was a period of first rains, second rains, then it's post rain, and then it kind of recharges itself. And what I wanted to point out is really this drying out of the atmosphere that occurs after the rain, the drying out of the atmosphere, and then it's as if that moisture content sort of recharges in the atmosphere. Probably what I really wanted to point out most in this plot is the shear in the atmosphere. So these are the winds, the surface winds or the lower atmospheric winds, and that's the upper atmospheric winds. And there's a very strong shear here. And that level at which the shear occurs actually rises during this ISO event. Okay, so as the winds intensify, that level of the shear rises. And the reason I'm showing this to you is I was wondering whether this convergence has something with the rising of that shear level, and that's what affects the height of the clouds more than actually the total amount of rainfall. So that's again just a hypothesis. This is showing you a wind, and this is showing you pressure and moisture and temperature anomaly during this ISO event. So you can see heavy rainfall and then the drying out of the atmosphere, which you see here in the low moisture, and this cooling. So warming, high moisture, drying out after the rains, and cooling of the air. Okay, so with that I'll end. I think this analysis for us raises lots of questions. It's not a paper, it's only a talk, so any of my interpretation may be wrong, but I'd be very interested in talking to some of you about this. You know, what is the role that SST is playing? It's not entirely clear to us after we see this analysis. Thank you.